Okay, Bismillahirrahmanirrahim. Wassalatu wassalamu ala Rasulillah. So today we will solve review problems for chapter 13, 14, and 15. Okay. Chapter 15, I already recorded the video with the previous section. So please have a look at them. And by the way, at the end of this week, I will post mock exam on Blackboard for your own practice. Mock exam and their solution. So this problem is a very important problem, and I already solved it in the previous section. So please watch the recording. I will post the recording there. It's a very important one, by the way, A+ type problem. This one as well, okay? Watch the recording. This one as well, very important. The solution is here. Watch the recording. This one as well, very important problem. And the recording is on Blackboard. Watch it. This one, okay? It's a very important problem. Okay, maybe let me solve these two. Okay, let me solve these two, and then I'll go through something else. So here we have a graph in which we have an acceleration time graph. Okay, I have acceleration in meter per second square per time graph. So for a spring block system that oscillates in a simple harmonic oscillation, in a simple harmonic motion, find the amplitude of the oscillation. So I have a spring, and the spring has a constant spring K. It attached to a mass M, okay? And I stretch it for a maximum distance of xm. Of course, this is my relaxed position, and I release it. Of course, it will be oscillating between minus x max and plus x max, going back and forth. Okay, if I don't have friction, it will be going back and forth without any loss in energy. Now here, I gave you the acceleration time graph, and the question is find the amplitude of oscillation. So you know that it's a simple harmonic oscillator. I have x at any time is x max cosine omega t plus phi, right? So if I take the derivative, I will find the velocity of the block anytime. It's the time derivative of position with respect to time. So it will give you minus, omega will come out. Of course, derivative of cosine will give you a sine. So minus omega x max sine omega t plus phi. Second derivative will give me the acceleration, or first derivative of the velocity with respect to time. It will give me minus omega square xm cosine omega t plus phi. Okay, good. And by the way, here, let me just remind you that the maximum velocity or the amplitude of the velocity is just omega xm. Write it down. And the amplitude of the acceleration, the maximum acceleration, because this cosine is between -1 and +1. So the maximum of the acceleration is omega square xm. Okay. Good. Now here, what I gave you is acceleration time graph. So you can read what is the maximum acceleration. What is the maximum acceleration? 0.2. So AM is 0.2 meters per second square. Okay, this is AM. I can read it from here. And this is minus AM. Okay. And this is equal to what? Omega square XM. The question is, what is XM? So that means if I get omega, I get what is XM. How to get omega? As you know, omega is 2 pi divided by the period. I have to identify what is the period of my oscillation here. I started here. I went down to minus AM and goes back to 0 and finish at the same position. So my period is this time. Is the time I take for a full oscillation. The period is 0.8 seconds. And 0.4 seconds is half the period. Okay. And 0.2 is 1/4 of the period. So I know omega. Omega is just 2 pi divided by 0.8 seconds. I will plug it here. So I know what is xm. Xm is just A max 0.2 divided by omega square, which is this number here. And then I do it and I get my right answer. Now let's look at this problem here. I solved it in the previous section, but let me solve it again because it's very important. This is a physical pendulum. Physical pendulum is anything, any object with a mass, and I put a pivot point at one point of the object different from the center of mass, and I deflect it a little bit, small angle approximation, of course. Small angle theta, and I release it, of course, it will be oscillating around this pivot point. Okay. If the pivot point is at the center of mass, I will not oscillate. And I explained to you why yesterday. Okay. Now, let's read this problem. I have a uniform solid disk performing a simple harmonic motion in a vertical plane. The disk is pivoted about a frictionless pin through a point r divided by 2 from the center of mass, and the period of oscillation is t. So when the pivot point is here, at the distance r divided by 2 from the center of mass, the period is t. Okay. So my pivot point is here. I deflect it, so this is a pivot point here. I deflect it a little bit, small angle, and I release it. It will be oscillating around this vertical direction. Okay. Simple harmonic motion, because it's a pendulum small angle approximation, it will be a simple harmonic motion. Now the question is, what is the new period if the disk is pivoted at the rim? Now, if I shift the axis of rotation from here to here, from here basically to here, this is my new pivot point. What is the new period compared to the old period? Okay. So we have demonstrated in class that, and this is in your formula sheet, for a physical pendulum, T is 2 pi square root of moment of inertia of the pendulum around the pivot point divided by mass of the pendulum, GH. And H is the distance between the center of mass of the physical pendulum and the pivot point. So here H is equal to R divided by 2. And here H is equal to R. Okay. Now let me just focus on this first one. The period T is 2 pi square root of moment of inertia of this solid disk around this pivot point divided by mass GH, which is R divided by 2. Let me calculate it. The problem is to calculate this I around the moment of inertia or rotational inertia around the pivot point. Parallel axis theorem. It's moment of inertia around the center of mass plus mh square. So what is the moment of inertia of a solid disk if the axis is passing through the center of mass? Half mr square plus mh square. Now here h, as I said, is equal to r divided by 2 square. So if you do it, you will have half mr square plus 1/4 of mr square. So this will give you 3/4 mr square. Now let me plug it into my equation. I will have T is 2 pi square root of 3 divided by 4 mr square divided by mgh. H is r divided by 2. Let me write it r divided by 2. Of course, m will simplify. This is why the period of oscillation does not depend on the mass, because you have a mass at the moment of inertia, you have the mass on the denominator. And of course, I will simplify by this, and I will find what? T is 2 pi square root of 3 divided by 4 r divided by g. But I have a 2 here, so this 2 will go here, so I'll have 6 divided by 4, which is basically 2 pi square root of 3 divided by 2 r divided by g. And this is my period. Okay. Now what happens if I shift this axis of rotation from here to the rim or to the edge? The new period, I will call it T prime, will be 2 pi square root of I around the rim. Okay, so I around the new let me call it I prime, okay, divided by mgh. Now, I prime is parallel axis theorem, I around center of mass plus mh square. So I center of mass is half mr square plus mh here will be r, because this will be the distance between the center of mass and the new axis of rotation. So this will give me 3/2 of mr square. Okay, so now t prime will be just 2 pi square root of 3/2 of mr square divided by mgr. M will simplify, cos r will simplify, and then I will have 2 pi square root of 3 divided by 2 r divided by g. And you see that it's the same. So t prime is equal to t. So the first answer is the correct answer. Even if I shift the axis of rotation, the period of oscillation will be the same because of this geometry. Now, I will ask you another question. What should be the length of a simple pendulum? You remember a simple pendulum. This is the vertical direction. The rod is massless and the whole mass is focused at the bob. Okay? And the length is L. The question is, what should be the length of a simple pendulum that will have the same period? You know that the period for a simple pendulum T is 2 pi square root of L divided by G. Doesn't depend on the mass again. Okay? So this is the period for a simple pendulum. That means 2 pi square root of L divided by G should be equal to 2 pi square root of 3 divided by 2 R divided by G, multiplied by R divided by G. So that means that this RL should be equal to 3/2 of R. So the length of this simple pendulum should be 3/2 of R. And the period of these two objects, simple pendulum and physical pendulum, will be the same if the length is 3/2 of R. Okay. Now let's solve this problem. What do we have here? We have a block of mass 2 kilogram. That means 2 kilogram. I give you attached to a spring, constant spring, 200 Newton meters. So it's performing a simple harmonic motion in a horizontal frictionless surface. Okay, you know that x at any time will be xm cosine omega t plus phi. Now, when the displacement from equilibrium is 3 meters, I'm telling you that x at this time is 3 meters. The speed v at that time is 40 meters per second. And the question is, what is the amplitude of the motion, of the oscillation? What is xm? So what should I do here? I should use conservation of mechanical energy. Frictionless horizontal table, mechanical energy, which is kinetic energy plus spring potential energy, is a constant here, is half k x max square, with k is m omega square. Basically, omega is just square root of k divided by m. It's in your formula sheet. For a spring mass system, okay? For a pendulum, physical pendulum, what is omega? Omega is just square root of mgh divided by I. And this is why, because t, for a physical pendulum I'm talking about, okay? T is just 2 pi divided by omega. So that's why t is 2 pi square root of I divided by mgh. You can find it on your formula sheet because this is in your formula sheet. But in some problems, I will not ask you the period. I will just ask you what is the angular frequency. So you can get it from the formula sheet if you don't remember it from the class. Anyway, so this is our mechanical energy and it's constant. And the question is, what is this xm here? Okay. So k is just half mv square. I know m, I know v square. So I know the kinetic energy. Plus spring potential energy, half k, I know k, x square. I know k and I know x. So that means I know half k xm square. Because of conservation of mechanical energy, if I know the position, I know k, I know v, I know m, I know what is xm. Okay. And also I know what is omega, because omega will be just square root of k divided by m, which is 200 divided by 2. And I take the square root, it will be 10 radian per second. And you do that, you will find your xm is just 5. Okay? And this we talked about it yesterday, okay? Half mv square, half kx square equal to half kxm square, conservation of mechanical energy. Let me divide by the mass everywhere. And I divide by 1/2. The 1/2 can go away, of course. And I divide by the mass everywhere. So I'll have v square. If I divide by the mass, I will have k divided by m. But k divided by m is just omega square. And this is equal to omega square xm square. And this is very useful as well. Okay? If I know v, I know x, I know omega, I know what is xm. Okay? Good. Again, I have posted many recitation, many problems on chapter 10, and it's already on Blackboard. So you can solve them, understand them, and make good use of them. Now let's go to chapter 14. So what do we have here? We have water flows through the pipes shown in the figure here, figure 13. The water speed through the lower pipe is 5 meters per second. Okay, here you can see it, 5 meters per second. And the pressure that I read here, P1, is 75 kilopascal. In reality, I'm giving you the gauge pressure. Gauge pressure is absolute pressure minus atmospheric pressure. Basically, P1 minus P0 is equal to 75 kilopascal. But here, it doesn't really matter. I want you to use this. Okay? Now, the question is, what is the reading on the upper pipe? What is the pressure here at P2? Now, what I gave you here, of course, this is P1. Okay, this is V1. And I gave you here Y1. Let's say Y1 is 0. That means Y2 here is 2 meters above, is 2 meters plus 2. Okay. And here I am asking you, what is P2 first? But you know that before I get P2, I have to get V2. What is the speed of the fluid on the upper pipe? Okay. Of course, the problem is guiding me. I have to use Bernoulli equation plus continuity equation. Okay. I have water, incompressible fluid. It has all the 4 characteristics. I will look at the streamline going from here to here. So along this streamline, I can use the Bernoulli equation. It will give me P1 plus half rho V1 square plus rho GY1 is equal to P2 plus half rho. Here there is a rho. Half rho V2 square plus rho GY2. That means P2 is equal to P1. This is what I want, is equal to P1. I know what is P1. Half rho V1 square minus V2 square plus rho GY1 minus Y2. Y1 minus Y2 is minus 2. Rho, I know what is the density of water. 1,000 kilogram per meter cube. I know G, of course, we are on Earth. I did not say it, but you know that we are on Earth. 9.8 meter per second square. Okay. Now, how to get the speed? V1. V1 is known, is 5 meters. Now, what is V2? I will use continuity equation. A1 V1 is equal to A2 V2. That means V2 is just equal to A1 divided by A2 V1. Now, of course, it's a pipe. I assume that this pipe has a cylindrical shape. Okay, so A1 is just pi R1 square. And A2 is just pi R2 square, R being the radius. So the ratio V2 will give you, the pi will go away, and I will have what? A1, R1 divided by R2 square multiplied by V1. I know V1, it's 5. I know R1 is 3. And I know R2, it's 2. Okay, here I gave you the diameters. Okay, so the radius is half the diameter, of course. So I just gives me V2. Continuity equation gives me V2. V2 is 11.25 meter per second. So I know everything. I know P1, of course, in SI unit in Pascal. Half rho, I know rho, 1,000, okay? V1 square minus V2 square. And by the way, V1 is this, V2, you see, this is a mistake. It's 11.25. And this happens very frequently sometimes. Okay? There are typos, but now you are mature. You are at the end of Physics 101. After Physics 101, you can get merit, okay? Because now you are mature. You can handle anything, okay? Even 2 Ys, okay? Because of course now you get an A plus, inshallah. So, so here it's not a minus, it's a typo, it's a mistake. Okay? And then plus rho g. So I just take this equation, I know everything, and I know what is my P2, and I calculate it, and this is it. Okay. Bernoulli equation plus continuity equation. In general, you can use them in tandem, in pair, together. Now let's look at this problem here. We have a ping pong ball, and it has a diameter of 3.8 centimeters and an average density of 0.084 gram per centimeter cube. The question is, what is the force required to hold it completely submerged underwater? So this is my water. Of course, if I put my ping pong ball, it has, of course, a spherical shape. If I don't hold it, it will float because the density is less than the density of water. By the way, what is the density of water? Kilogram per meter cube. In gram per centimeter cube, what it is? One gram per centimeter cube, okay? Because here you have 1,000. Well, you know how to do it, right? Okay. Number 1, like chapter number 1, how to go from unit conversion. Anyway, so here, if I leave it, it should go up. Now I am holding it with a ball, with a force to keep it completely submerged. So the question is, what is this force required to keep it completely submerged? So what are the other forces that are acting on my ping pong ball? Of course, you have the weight of the ping pong ball, but also you have the buoyant force. So here I will have an equilibrium, okay? Balance of forces. Weight, mg of the ping pong ball, plus F that I want should be equal to the buoyant force. Okay. Good. So now what is the buoyant force here? Mfg. The buoyant force is equal to the mass of the fluid displaced by the ping pong ball. So Mfg is equal to what? Rho F Vfg. Vf being the volume of the fluid displaced by the ping pong ball. Now the volume of the fluid displaced by the ping pong ball, since the ping pong ball is totally submerged, is equal to the volume of the ping pong ball. Okay. Okay. Basically, it will be 4 pi divided by 3 radius of the ping pong ball cube. If I know the diameter, I know the radius. 1.9, 10 to the power minus 2, sorry, because I have to put it in meters. This is my radius of the ping pong ball. Okay. Good. So I know the buoyant force. Now what is F? Well, F will be rho F V ping pong ball multiplied by G minus the weight of the ping pong ball. And the weight of the ping pong ball is the mass of the ping pong ball multiplied by G. Mass of the ping pong ball is density of the ping pong ball multiplied by the volume of the ping pong ball multiplied by G. So I know everything now. Okay. So it will be what? So let me put as a common factor. I will have rho F minus rho object multiplied by VOG. Rho F, I know it already. Okay. Let me put it, I can put everything in gram per centimeter cube if you want, but I don't want that because this G here is in SI unit. So I have to keep everything in SI unit. Okay. So this rho here, rho of the fluid is rho water, 1,000, okay, kilogram per meter cube. Now, what is the density of ping pong ball in kilogram per meter cube? You multiply this by 1,000. Okay. So it will be 0.084 multiplied by 1,000, of course. Okay. What is the volume of the ping pong ball? 4 pi divided by 3 radius. Of course, the radius, you put it in meters. So 1.9, 10 to the power minus 2 cube. Okay. And then you multiply by 9.8. And this will give you the force that you need to keep the ping pong ball completely submerged. And again, I have posted these recitation problems, difficult, easy, very difficult one on Blackboard. So watch them, okay? So if you put the numbers and you use your calculator properly, this is what you will get. This is pi, this is the volume here, as I talked to you. This is the G, and this is the density of ping pong ball, and this is the density of water, and this is the density of ping pong ball, and you get this number. Okay. I want it in 3 significant figures, of course, right? Because I'm talking about 3 significant figures here everywhere. Okay, now let's look at this problem. A rate flow of water through a horizontal pipe is 4 meter cube per minute. In meter per second, what is the speed of the flow at a point where the radius of the pipe is 0.05 meters? So here I gave you a volume flow rate. RV is 4 meter cube per minute. Of course, I want it in meter cube per second. It will be 4 meter cube a minute is 60 seconds. And this volume flow rate is constant and is equal to cross-sectional area multiplied by the velocity of this or the speed of the fluid, a continuity equation. Okay. So I have 4 divided by 60 meter cube per second is equal to A. What is the cross-sectional area? If the pipe has a radius of this, of course, the pipe is naturally cylindrical. Okay. So the cross-sectional area is pi r square, 0.05 square. By the way, why we don't design pipes that are, rectangular, or, the cross-sectional area is rectangular? It's not very, engineeringly speaking, it's not very favorable, okay? You will be having a lot of bubbles, okay? So it's easier to have a cylindrical shape, for the dynamic than having a rectangular shape or parallelepipedic shape. Of course, that's just by nature, okay, because of the symmetry of the cylinder, multiplied by V. So I know everything. My only unknown is V here. Okay. I just divide by the cross-sectional area and I get V. Okay, and it gives me 8.5 meter per second. Now, let's look at the hydraulic lever. What time is it? Okay, so we have a piston here, and I give you the diameter of the piston, meaning I'm giving you the cross-sectional area. Plus you get the radius, okay, which is half of this diameter. Okay, so 1.9 centimeter. And then I have a larger piston, and I give you the larger diameter. So you can get to the radius to get the cross-sectional area. Okay. Good. Okay, now the question is, what is the magnitude of the small force F on the small piston that is needed to balance a larger force F, which is 15 10 to the power 3 Newton. So basically in this larger piston, I have a car. Okay. Let's say, a car, small car. and this weight is on here. So if I leave it as it is, what will happen? Of course, it will move, the piston will move down. So I have to counterbalance that. But here I have to use a small force because I have a smaller cross-sectional area. So what should be the small force? We will use Pascal principle. It's an incompressible fluid. It's a hydraulic press. The change in pressure is the same. So that means what? That means F divided by the small cross-sectional area A. This small a, by the way, small a is just pi r squared. This is equal to capital F divided by the large cross-sectional area. And the large cross-sectional area here is pi capital R squared. Okay. So that means the small cross-section, small force is just F divided by A multiplied by A. So let me put it. So I will have 15 10 to the power 3 Newton multiplied by A. Of course, the pi will go down. Okay, so here, this ratio A divided by capital A will be just the ratio of the radius, basically small radius divided by big radius square. Okay, so here, of course, the radius I can multiply by 2 up and down, I will get the diameters. So let me keep the diameters as they are, because I know that they will cancel, it's unitless, right? So I will have small diameter 3.8 divided by 53 square. And you do it, you will get a small force. Basically, this can be what? This can be a force roughly of a 7 kilogram object. So a 7 kilogram object can keep in equilibrium a car, a small car. Okay? Just using Pascal principle. Okay? A small force which is transformed into a larger force. Okay? Normally it should move, but here I want it to be balanced. Okay? So if I apply a small force here, I should move it up here. But here, of course, I want it to keep static. This force up will be balancing the weight of the car. Anyway, this is a very simple problem. Okay, that's what I want to say, and you get it easily. Any question? We have solved this in class many, many times. And if you watch the recitation video, we have solved this as well. If you don't have another question, let's go now to chapter 13. Again, chapter 13, I posted on Blackboard 2 excellent recordings, okay, of recitation problems. So make good use of them. I have looked at the attendance there. Unfortunately, half of the students did not watch it yet. So I encourage you and I urge you to watch these recitation videos. Okay. Good. And by the way, yes, some of you, mashallah, got full mark in the classwork grade, mashallah. Congratulations. Yeah. So some of you got full mark, especially in this section. And by the way, he is here. Let me see. Oh, yes, I see him in the attendance. Okay. Now let's look at this problem here. Chapter 13. So we have 4 masses that are arranged with their center of mass on the x-axis. You see here, I have M1. It has 5M, okay, and the center of mass is here. Then I have M2, as you can see it. It's a spherical shell, an empty sphere, okay, and it has a mass 10M, okay. And then I have M3, which is here. Outside the first sphere, but inside the second sphere. And then I have M4, which is outside both of them. And all of them are aligned. The center of mass of this center of the 2 shells is aligned with these 2 particles, M3 and M4, and they are on the x-axis. And here I show you the distance. The radius of M1 is 50 kilometers. Okay? This distance here is 50 kilometers. And the radius of M2 is 120. Okay, let me do it this way. This is 0. This is 50 kilometers. This is 120 kilometers. Okay, and M3 is located at 80 kilometers, right? That's what I said. M3 is located at 80 kilometers, okay? Let's put it here. M3 is located at 80 kilometers. And M4 is located at 320 kilometers. 320 kilometers. Now, what is the mass of M4 such that the net force on M3 is 0? Now, I want to look at M3 here. What is the net force on M3? So how many forces do I have on M3? Omar Al-Shamari.
Yes.
How many forces do I have on M3? MashaAllah. The first time I hear your voice. Tabarakallah, MashaAllah. Yes. Go ahead, Omar.
Basically 2.
Okay, simply 2. Which one?
From the shell, the smaller shell.
Excellent.
And M4.
And M4. Why I don't have a force from M2?
Because M3 is inside the bigger shell, so the net force is 0.
Exactly. So it's a shell theorem. So this M2 does not apply a force on a particle which is within it. Okay. So there is no force on M3 from M2. I only have 2 forces. I have the force from this small shell and the force from M3. And you know the gravitational force is Gmm divided by the distance square. Okay. So here's the net force should be equal to 0. And I want, here I will have 2 forces, of course, F on 3 by 1 plus, let me put it in vector, plus F on 3 by 4. Okay. One of them is positive, this is a positive direction, and one of them is negative. So if I look at along the x direction, I will see that net force, which should be equal to 0, will be what? F on 3 by 1. That's negative. That's minus G M1 M3 divided by the distance square. What's the distance here between these two? 80 square. Of course, technically I should put everything in SI units. Okay? But if you see here, you know, I want the mass not in kilogram, but in terms of M. So I can leave it as it is, okay? Because these distances will cancel each other. Okay? And then I will have plus F on 3 by 4. So it will be G M3 M4 divided by the distance between them square. What's the distance between them? You have to take 320 minus 80. Okay? So this gives you 240 square. Okay? And this should be 0. And you play with it and you will get your, you see here, you have a ratio of the distances. Of course, the G will go away. The G is not 0, okay? So you will simplify by G. But also the units here will, you can leave them as they are in kilometers because you will have a ratio of units, okay? And you will have M4 should be 45 M. Good. Now let's look at this problem here. So who else I never heard during the semester? Muhammad Al-Garni. I think I never heard from you, brother. I had good students, many good students last semester. At the end of the semester, they got A+, mashallah. And I told them, how come I never heard of you? They said, okay, because I'm a, you know, kind of shy, quiet guy, that's why. And that reminded me myself when I was a student, okay? I was kind of shy. Anyway, now I'm not anymore. Okay, so let's look at this problem here. Muhammad, what do we have here? we consider a planet which is in an elliptical orbit around the sun, and the sun is here. Okay, let me change my, okay. And the planet is at different location A, B, C, and D as indicated in the figure. A is here, B is here, C is here, and D is here. So at which location is the orbital speed of the planet around the sun the minimum? Muhammad.
D maybe, because it's so far from the sun.
Excellent. This is what we call an aphelion. And this is what we call the perihelion. Okay. So you know that law of Kepler number 1, elliptical orbit. Okay. Let's assume that I'm rotating the orbit, the planet is rotating around the sun in the positive direction, counterclockwise. Let's assume that. Okay. So first it's an elliptical orbit and the sun is at one focal point. Second law, the second law of Kepler is telling you that the area swept in same interval of time is constant. And if you remember in class, I told you this is constant because you have constant angular momentum. Angular momentum of the planet is the same. So we demonstrated in class that dA over dt is just angular momentum of the planet divided by 2 times the mass of the planet. So now if I have conservation of angular momentum, then I will have conservation of the area I sweep per unit time, dA over dt, and again, A is just the area swept by the line that joins the planet and the sun, okay, per unit time. That area swept per unit time is constant because of conservation of angular momentum. Okay. So write down this. In some problems, I will give you this area, I will give you the mass of the planet, and I will ask you angular momentum. Sometimes I will give you dA over dt, I will give you angular momentum, and I will ask you what is the mass of the planet. Now, what is the angular momentum of the planet? Of course, the angular momentum of the planet can be considered as a single particle. So it will be what? Basically, the magnitude of R cos P. Okay. So the magnitude of R cos P is R P sine phi. Okay. It will be R mv sine phi. Okay. Let's say this is R. It joins the sun and the planet. And let's say V is somewhere here. Phi is the angle between them. In general, this angle phi, I don't really know it. Unless I am at these two positions here. Here, of course, V and R are perpendicular. And here also V and R are perpendicular. Now, if I have conservation of angular momentum, of course, a larger R, a larger distance corresponds to a smaller V. Okay? When I'm far from the sun, as you said, Muhammad, I go slower. When I'm close to the sun, like at the perihelion, I go much faster because I have to respect the conservation of angular momentum. Okay? And the joke I used to say to my students, this is the exam and the student is the planet. When the student is coming next to the exam, he accelerates. Okay? And then after the exam, he starts becoming lazy and he decelerate. So now I will ask you another question here. On which quadrant will the planet accelerate or decelerate? So first of all, I have to tell you that the planet is rotating, let's say, counterclockwise in the positive direction. So it's going in this direction. So you will see that when the planet is going in the counterclockwise direction, from here, the planet is decelerating. Now, because from here, the distance becoming larger and larger and larger and larger. So the speed is getting smaller and smaller and smaller and smaller. So in this upper two quadrants, I am decelerating. And then in these two quadrants down here, the distance becoming smaller and smaller and smaller, and I go faster and faster and faster and faster. And this is the fastest point. Okay? So you are here, the exam is here, far from the exam, okay, you decelerate. And then when you arrive here, you start accelerating. Okay? And this is the fastest point. And this problem can come in many different forms. Something else that I want to talk about in this problem. So I told you that I have conservation of angular momentum due to the second law of Kepler. Now, I also have conservation of mechanical energy. Okay, because the planet, you can assume that basically the planet is going around in the void, interstellar void. Okay, there is no friction. Okay, because the planet and its environment is just moving around a vacuum, let's say. So you don't have friction, so you have conservation of mechanical energy. Who can tell me what is the mechanical energy of an elliptical orbit that has a semi-major axis A? What is the mechanical energy of a planet which is going around in an elliptical orbit? Yeah, Omar.
Minus G sun.
Minus G, mass of the planet, mass of the bigger astronomical body divided by
2A.
2A. Excellent. And this mechanical energy is conserved. It only depends on the A. Okay? And of course, it depends also on the masses, but these two masses are constant. So this is a constant. Okay? I told you that angular momentum is constant, but also mechanical energy is constant. And mechanical energy is constant means what? Mean kinetic energy plus gravitational potential energy, the sum of them is constant. Kinetic energy is half m mass of the planet, speed of the planet square. Gravitational potential energy is minus g m divided by r. Now you see, this is like a spring. Okay. In some problems, I will give you v. For instance, I will tell you, oh, the v here is this value, 55 kilometers per second. And the r here is this. Let's say how many, 10 to the power 15 meters. And I will ask you what is the semi-major axis. Okay. Because I'm giving you, by giving you v, I'm giving you the kinetic energy. By giving you r, I'm giving you the potential energy. And then the only unknown will be a. Of course, I will give you the mass of the sun at least. Okay. Because you will see that the mass of the planet will kind of simplify. Okay? Or the mass of the planet. I'll give you both masses. Good. What time is it? 1 minute. Okay. So now, I have two identical spaceships, A and B, in a circular orbit. Now I have a circular orbit. Now, if I have a circular orbit, the mechanical energy is also conserved. Gmm divided by 2r, because the difference between a circle and an ellipse, I just replace the radius, which is constant here, by the semi-major axis, which is a. But when I have a circular orbit, I have a uniform circular motion, because when I fix the r, I am fixing the v. The kinetic energy is half mv squared, but v is what we call an orbital speed, and it's gm divided by r squared. Divided by r, and this is v squared. Okay? And we demonstrated this in class. If I have a circular orbit, the speed does not depend on the mass of the spaceship. The speed just depends on the distance between the spaceship and the astronomical body. And we show this in class. Now, plus, of course, the gravitational potential energy, which is gm divided by r. Okay? But when I have this r is fixed. So I have a uniform circular motion. So a circular orbit is basically a approximation. Okay? And that's approximation, it's nice. And I have a uniform circular motion. And in a circular orbit, I showed you that Of course, UG is minus GMM divided by R. Kinetic energy, which is half mv squared, is just GMM divided by 2R. And mechanical energy, you add them, will give you minus GMM divided by 2R. Mechanical energy in a circular orbit is just minus the kinetic energy. But this is only true for a circular orbit. Okay? This is only true for a circular orbit. In a circular orbit, the V is constant. Its orbital speed is Gm divided by R. And we demonstrated this in class. So unfortunately, I will not have time, but here this is simple. All what I will do is I will just use the third law of Kepler. T square is 4 pi square divided by Gm multiplied by the radius cube. And you will use it, okay? You will use also the mechanical energy, and you will use the period, and then you will get the ratio of the mechanical energy. Anyway, so it's time. Let me stop here. It was a very, great pleasure teaching you Physics 101. Bismillahirrahmanirrahim. Wassalatu wassalamu ala rasulillah. Assalamu alaikum. So we will solve review problems, as I said, from the last 3 chapters, chapter 13, chapter 14, and chapter 15. And at the end of this week, I will upload a couple of mock exams on Blackboard for your own practice. So in the other sections, I solve these problems, okay? So I will put the recording of this problem. It's already there, by the way. I will put it on Blackboard. They are important problems. This is an, let's say, A plus or A type of problem, okay? That is interesting. This one as well is very interesting. This one is excellent. This one, I will come back to them at the end if I have time. But let me focus on what I did not have time to solve with the other 2 previous sections. So discard, let me discard this. Okay, let me start by the end. Okay, this is chapter 13. Let's start by this problem. Gravitation. So I have a spherical planet, and I give you the radius of the planet, 400 kilometers. So 4×10⁵ meters. And this planet has a gravitational acceleration of 4 meters per second square at the surface of the planet. Find the escape speed of the planet. So you know that the escape speed, this is in your formula sheet, is square root of 2g mass of the planet divided by radius of the planet. Okay. Sometimes the planet, sometimes, anyway, mass of the astronomical body divided by the radius of the astronomical body. Okay. It does not depend on the mass of the object that I want to, throw away from the planet. So it just depends on the mass of the planet and the radius of the planet, not on the small m, the mass of the object. So how did we get this? You know that escape speed, I have my object, it has a radius r, mass m, I have my object here at the surface. I launch it at escape speed. If I launch it at escape speed, it will go to infinity. At infinity, kinetic energy is 0 and potential energy is 0. So at infinity, of course, mechanical energy is 0. So I can use conservation of mechanical energy between the surface of the planet and infinity. Mechanical energy initial is equal to mechanical energy final, which is at infinity, which is 0. So I will have half mass V escape square minus GMM divided by R. This is equal to 0. And this gives you this escape speed, which is in your formula sheet. Okay. So I know the radius of the planet. It's here, but I don't know the mass of the planet. I will get it using the gravitational acceleration. I know that the gravitational acceleration, AG, at the surface of the planet is equal to 4 meters per second square. That means you know what is the gravitational acceleration is gm of the astronomical body divided by r square. Okay. So here the r is capital R because I'm looking at the gravitational acceleration at the surface of the planet. In other words, of course, m will be r square ag divided by g. This is the mass of the planet. I will just plug it here inside. So v escape is square root of 2 g m. Now m I will replace it by its value, of course, r square ag divided by g, and then here I will have another r. Of course, the g goes away. This r and this r simplify, and I have just my escape speed, which is 2 times r ag. Okay, square root. Of course, ag is 4. R, I know it. Okay. So, and then I will get my escape speed, and it will give you 1.8 10 to the power of 3 meters per second. So 1.8 kilometers per second. Okay. So you start from the escape speed. It's in your formula sheet. If you don't remember or you don't see it in your formula sheet, let me check. Yes, it's in your formula sheet, but you know that it's coming from here. Okay. And then this, you know it. Okay. Gravitational acceleration. Let me write it here. At any distance r is just gmm divided by r square. Gm, sorry, m of the. And where it came from is coming from the gravitational force, which is gmm divided by r square. And if I apply Newton's second law, it's mass multiplied by the gravitational acceleration. So that means the gravitational acceleration is everything without, of course, a small m. Okay, good. Let me say something also very important. You know that the radius is just capital R plus altitude h. The distance between the center of the planet and the object is just equal to the radius of the planet plus the altitude h. Altitude is the distance from the surface of the planet. Okay. And again, I have posted two extensive videos on chapter 13 on Blackboard. And I did the same for chapter 14, and I did the same for chapter 15. If you do it, inshallah, the final exam will be a piece of cake. If you solve all these problems, of course, and you understand them, you understand the recitation. Okay, now let's go to this problem here. What do we have? We suppose that a drill is able to reach a depth below the Earth's surface equal to 10% of the radius. Okay, what is the acceleration due to gravity at this depth? Acceleration due to gravity is just g mass of Earth divided by r square, r being the distance between the center of Earth and the object. So here r is 10% below the Earth's surface. That means r is equal to 90%. So 0.9 multiplied by the radius of the Earth. Okay, the distance between the center of Earth and where the object is 0.9, 90% of the radius of the Earth. Now, if I want to calculate the gravitational acceleration at that position, I will say that it will be equal to g. Now, this mass will not be the mass of the Earth, will not be the total mass of the Earth. It will be the mass inside divided by r square. Mass inside being the mass of the, let me put it here. This is the Earth. Okay, it has a radius r. My object is somewhere here. Okay. So this is the inner sphere, right? So I need to get the mass of this inner sphere such that if I have my gravitational acceleration here, it will, because the shell theorem, okay, the external part will not attract the object. Okay? Only this inner sphere will exert a gravitational force, a gravitational acceleration on my object. So this is mass inside. Mass inside is the mass of this. Now, how do I get the mass inside? We did it many times in class. You have to use the density of the Earth to consider that the density of the Earth is constant, which is an approximation, as I told you. So it's mass inside divided by volume inside, which is equal to the total mass of the Earth divided by the total volume of the Earth. So that means mass inside will be mass of the Earth multiplied by volume inside. What is the volume inside? It's a sphere, 4 pi divided by 3r cubed. What is the total volume? 4 pi divided by 3 capital R cubed. Okay. In other words, mass inside is just mass, total mass of the Earth. Of course, I simplify by this, and I will have R divided by capital R cubed. So basically, it will give you 0.9 cube multiplied by M. Okay. Now, let me come here and do it. So AG at R equals 0.9 capital R is G, mass inside. I will replace it by total mass multiplied by 0.9 cube divided by R square. R square, I will replace it by this. So I'll have 0.9 multiplied by capital R, of course, square. So this will give me what? 0.9 cube divided by 0.9. So I have 0.9 multiplied by GM divided by R square. But what is GM divided by R square? This is just AG when R equal to the radius of the Earth. Okay, basically GM divided by radius of the Earth square is 9.8. This is a gravitational acceleration at the surface of the Earth, 9.8 meter per second square. So what I'm looking for is just 0.9 multiplied by 9.8 meter per second square, and this will give you 8.8 meter per second square. Okay, now let's go to the next type of problem in chapter 13. And again, this is also in the video that I posted on Blackboard, but let me just do it again. Okay. So we have two identical ships, okay, same mass, but they are in circular orbit. Again, I tell you that circular orbit is what? Is an approximation. Okay. In reality, orbits are elliptical. For instance, the orbit of the Earth has a very small eccentricity. So we can approximate the orbit of the Earth around the sun like circular. But in reality, it's elliptical. Okay. But a circular orbit is, just very pragmatic. So if I have a circular orbit, let me just remind you, circle versus ellipse. In a circle, I have radius r, which is constant. I will replace it by the semi-major axis if I have an ellipse, which is constant. Okay. So what is the mechanical energy if I have a circular orbit? Anyone? It's in your formula.
G m over 2r.
Excellent. Negative G m over 2r. And what about the mechanical energy if I have an ellipse? I just replace r.
Just replace r
exactly.
with a.
Excellent. So G m divided by 2a. Okay, let me just remind you a few things here because this is important. Okay, why do I have this in a circle? Of course, in a circular orbit, r is constant. R being constant, actually, I have a uniform circular motion. If I have a circular orbit, I have a uniform circular motion. Okay, so if I have a uniform circular motion, that means the speed is constant, the orbital speed. And we demonstrated in class that the orbital speed is just g m, mass of the biggest astronomical body divided by r. It does not depend on the mass of the ship or the mass of the object. It just depends on the mass of the astronomical body and how far the satellite is from the astronomical body. A given radius will give me a certain orbital speed. Okay. And if you don't remember how we get this, it's just coming from the fact that gravitational force is gmm divided by r square. And the gravitational force for my satellite is my centripetal force. So it's equal to mv square over r. Okay? So I use this, I get rid of the m, I get rid of this r, I end up with v square, which is my orbital speed square, is gm divided by r. It's different from escape speed, by the way. This is an orbital speed. I am in a circular orbit and rotating with constant speed if, of course, r is constant. So getting this gives me, of course, kinetic energy, which is half mv square. So half mv square will give me half m gm divided by r. So kinetic energy, if I have a circular orbit, is just gmm divided by 2r. And I know that gravitational potential energy is minus gmm divided by r. Mechanical energy, I add them and I'll find that minus gmm divided by 2r, which is minus the kinetic energy. Okay? Or which is 2 times the gravitational potential energy. And this is true for a circle. Anyway, now let's come back to my problem. Here I have these two. This is just a reminder, a quick reminder. Okay. Now, they are orbiting around this planet X. Okay. So the mass of the astronomical body will be the mass of X. Okay. So let me write it here. MA is equal to MB is equal to M. And capital M is the mass of the planet X. Now here I give you the period of the spaceship of A, which is 3 hours. So TA is equal to 3 hours. And TB is equal to what? 24 hours. And I give you this period of the spaceship B is 24 hours. Okay. So basically it's how many times TA? 8. So now the question is, what is the ratio of the mechanical energy for spaceship A to spaceship B? Okay, let me do it here. Mechanical energy for spaceship A is equal to what? Minus GMM divided by 2RA. Mechanical energy for spaceship B is minus GMM divided by 2RB. If I take the ratio EA divided by EB, the minus goes away. Of course, GMM goes away. Of course, this 2 goes away. So you will end up with RB divided by RA. Okay, they have the same mass. Of course, the mass of planet X is the same. This 2 is the same, etc. Now the question is, let's get this ratio of orbital radii. I will get them using, of course, the period. I will use third law of Kepler. TA square is proportional to RA cube, and the coefficient of proportionality is 4 pi square divided by GM, M being the mass of the astronomical body, mass of the planet here, MX. And of course, TB will be 4 pi square divided by GMX multiplied by RB cube. Okay. Now, I want RB divided by RA. So I will take the second equation divided by the first equation. So I will have TB divided by TA, okay, which is equal to 8, by the way, because I know that TB is 8 times TA. Of course, this coefficient of proportionality will simplify, okay? And then I will have what? RB divided by RA cube. Okay. Am I right or wrong? Oh, yes, I forgot here. I forgot the square here. Okay. If I take the square, of course, because it's TA square. So here, forget TB divided by TA square, of course. So 8 square. Okay. So I end up with 64, which is 8 square, is just RB divided by RA cube. Okay. So that means how much is RB divided by RA? 4. And then that's my answer. Okay. EA, mechanical energy A divided by mechanical energy B is equal to 4. Okay. Now, let me go to this problem. So this problem is straightforward, but let me just spend time quickly. So we consider a planet which is in its elliptical orbit around the sun at different location A, B, C, and D as indicated in the figure. The question is, at which location is my orbital speed around the sun minimum? So it will be D, of course. Why? Because actually I have an elliptical orbit and I have what? Conservation of angular momentum. Okay. But also I have conservation of mechanical energy. I'll come back to this just in a second. So here it's an elliptical orbit. This is my semi-major axis A. Okay, this is the sun. So the lines that connect the sun to the planet sweeps out equal areas during equal time interval. If you remember in class, we said dA divided by dt, the area that this line is sweeping divided by time interval is constant. And I told you that it's equal to the angular momentum of the planet divided by 2 times the mass of the planet. Write this down. Sometimes I will give you this area per unit time, and then I will give you the angular momentum, and I will ask you what is the mass of the planet. This is the second law of Kepler, law of areas. Now, here, okay, here, since of course angular momentum is conserved, this dA over dt is conserved, is a constant of motion. So angular momentum L of the planet is constant. What is the angular momentum of the planet? Well, the planet can be considered as a point-like particle. Angular momentum magnitude is just magnitude of r cos p. Okay, so it will be r cos dot p sine phi. So it will be r mv sine phi. So if r is this, the distance between the center of the sun and the planet, and v is this, the angular momentum is just the magnitude of r multiplied with the magnitude of mv multiplied by the sine of this angle. The sine of this angle is a little bit tricky. In general, it's unknown with exact precision. I can get it, but it's complex. But when I am at the perihelion or at the aphelion, by the way, this is a perihelion, the smallest r. Here's a v is maximum. Okay. And here's a v is minimum. Okay, minimum. Okay, but at these 2 points, I have 90 degrees, so I know exactly what is the angle. But what I want to say here, since the angular momentum is constant, a higher r will give me a smaller v. Okay. If I'm very, very far from the sun, which is here, this is the farthest distance from the sun, so I will have the smallest speed. This is the closest distance to the sun, and I will have the highest speed. Okay. And here I will say something, I'm rotating in the counterclockwise direction. Okay. Let's say that I'm rotating in the counterclockwise direction. That's why the V is up here. If I was rotating in the clockwise direction, it will be the opposite. The V will be down here and the V will be up here. Okay, bottom line, R large, V small, R small, V large. So actually I'm accelerating and decelerating. So if I want to ask you the same question but differently, I will ask you, assume that this planet is rotating, let's say clockwise. All the planets in the solar system are rotating counterclockwise, okay, in this direction, except one. No. All of them are going back, except one which is rotating around itself clockwise, but that's another story. But here I will not look at that. I'll say that, let's assume that the planet are rotating this direction, in the negative direction, clockwise. Okay. Now my question is this: in which quadrant is my planet accelerating? Okay. So these are the 4 quadrants. Okay. Let's say this is my 0, this is X, this is Y. The semi-major axis is A. So I want to know in which quadrants is my planet accelerating? And in which quadrant is my planet decelerating?
The first and the fourth?
Accelerating or decelerating?
Accelerating.
Accelerating. So you said where?
The first and the fourth.
The first is here, first, second, third, and fourth. Okay. Now,
If it's clockwise.
if it's clockwise. Okay, so let's assume that it's rotating clockwise. It's rotating this way. Okay. Now let's look at it. Of course, if it's rotating clockwise, when I reach here, this is my largest speed. And from here, the distance keep increasing, you see? It's increasing. So that means I'm decelerating. The distance, if I'm here, I'm rotating clockwise, and I start from here, the R is increasing, that means the speed is decreasing. And now when I reach here, now the distance start decreasing, and I start increasing the speed. So bottom here, I'm decelerating. I'm decelerating in the 3rd and 4th quadrant, and I'm accelerating in the 1st and 2nd quadrant. Okay. So I am accelerating here. Sorry, I'm decelerating here and accelerating here. Okay. If I'm rotating counterclockwise, you will just inverse it. Good. Now, what I used to say to my students is basically, when I am rotating now clockwise, let's say counterclockwise, in the positive direction. So you see, now R is increasing. So that means I'm decelerating on top. So V is slowing down here, but I'm accelerating here because here R is getting smaller and smaller and smaller and smaller. So I'm accelerating here. V is increasing here. So what I used to say to my students, this is the exam here. And the student is a planet. Okay. When the student is here and the exam is here, so the exam is getting closer. He's getting closer and he's going faster and faster and faster and faster. Now he completed the exam. The day after exam, he started becoming lazy and decelerating slowly, 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 slowly. And then when he arrived here again, he started accelerating again. And I sent you a nice video about, this motion, okay? But although I'm accelerating and decelerating, I have a constant period, okay? And you can demonstrate it, but you have to use integrals. Anyway, okay. Now that's it. Okay, this problem, I solved it with the previous section, so I will skip it. Okay, if you don't mind. And I will go to, let's say, what time is it? Okay, 27. Let me go to chapter 15, and then I will come back to chapter 12, or to chapter 14. Okay. So let's look at this problem here. What do we have? We have an object, and I give you the mass of the object. This is chapter 15. M is equal to 3 kilograms, and the object is in simple harmonic motion in 1 dimension and move accordingly to this equation. So here I gave you X max. This is omega. Of course, this is phi. x at any time is x max cosine omega t plus 5. X max is 5, omega is pi over 3 radian per second, and phi is minus pi over 4. So t is in second. Now the question is, how much time is needed for the object to move from its equilibrium position, which is x equals 0, relaxed position, to a position where the potential energy is half of the total energy? Okay, so the question is, what is delta t? Basically t final minus t initial. Okay, when x initial is 0 and x final, which is basically x at t final, is, I don't know, but I have to get it. But I know that at x final, I know that potential energy, which is US, is half the total energy, which is half capital E, the mechanical energy. Okay, let's go. First thing first, I have to find TF and T initial. Okay, so x initial is 0, meaning x at T initial is 0, meaning xm cosine omega, which is pi over 3 T initial minus pi over 4, this is equal to 0. So this is 0 if this cosine is 0. Okay, and that means cosine is 0, of course 0 is just cosine pi divided by 2. That means this argument here, pi divided by 3 t initial minus pi divided by 4 is equal to pi divided by 2, such that the cosine is 0. I simplify by pi and I get my t initial, which is just half plus 1/4 multiplied by 3 seconds. So this t initial will give me 4 multiplied by 3, so 9 divided by 4 seconds. This is the initial time. Okay. Okay. So x is equal to 0 at t equal 9 divided by 4 seconds. Now, second question is, what is t final? Before I find t final, I have to find x final. But how do I get x final? I pass by the condition. The condition is US, which is half kx square, is equal to half total energy, which is half E. I remind you that the mechanical energy is the kinetic energy plus spring potential energy is a constant, is half k x max square. Okay, so here I have to find US, which is half k x square, should be half of E, which is half k x max square. So I can simplify by k, I can simplify by half, and I find that x square should be x max square divided by 2, meaning x is just plus or minus x max divided by square root of 2. Let me take the positive value. I can also take the negative value, I don't mind. Okay. Because here this time will be absolute value. Okay, let me take the positive value. So x at time tf is equal to x max divided by square root of 2. That means x at time tf is just x max being 5, cosine omega, which is pi divided by 2, tf minus pi over 4. Okay. So now I have to solve this trigonometric equation here. If I simplify by x max, I will get that cosine pi divided by 3 t final minus pi divided by 4 is equal to 1 divided by square root of 2, which is square root of 2 divided by 2. Which angle has a cosine square root of 2 divided by 2? pi over 4, right? So I will end up with pi divided by 3 T final minus pi divided by 4 is equal to pi divided by 4. And of course, I can do this modulo 2 pi, but here I'm looking at the smallest one, smallest angle that will give it to me. I will simplify by pi, so I'll get what? T final is just 1/4 plus 1/4, basically 1/2 multiplied by 3, so it will give me 3/2 of second. Okay, now I can calculate delta T, which is absolute value of T final minus T initial. So basically 9 divided by 4 minus 3/2. So basically 3/2 is 6 divided by 4 second. And this will give me 3/4 of a second, which is 0.75 second, which is the answer here. Okay. So here, the difficult part is not difficult, but is to translate this relationship here. Potential energy is half of the total energy. Okay. So you know that the total energy is constant. So which x, at which position do I have potential energy is half of the total energy. Okay. And if potential energy is half of the total energy, then kinetic energy is the other half, by the way. Okay. Because the sum of them should give me everything. So I will get what is a position. X basically is just equal to xm divided by square root of 2. This is the position at which potential energy is half of the kinetic energy. And then I use my formula and then I solve the trigonometric equation. Okay, now let me go to the second problem, which looks the same, but let's just solve it. Then I will go to pendulum. Okay, so here also I have a spring mass system. Okay, this is my spring. It has a spring constant K. It has a mass M. I mean, the mass has the object has a mass M. This is my relaxed position. I elongated for a distance x max. It can go from plus x max to minus x max. And it can oscillate. Okay, etc., etc. So just knowing this, I know what is my omega. Omega is just square root of K divided by M. We demonstrated this in class, and this is in your formula sheet. In your formula sheet is given that the period, which is 2 pi divided by omega, is just 2 pi square root of M divided by K. Okay. Now let's look at the question here. Starting from T equals 0, find the time when the kinetic energy is twice the potential energy. Here, be careful here. Okay, I gave you this x, and I did it, you know, on purpose. I put a sign. In general, I will always write my simple harmonic oscillator as xm cosine omega t plus phi. And I can transform a cosine into a sine. I can transform a sine into a cosine. I just have to add pi over 2 or retract pi over 2, depending on what I want. So it's just a mathematical key. So if you have choice, you use this. If now the problem imposes you to put a sign, you take it as it is, no problem. So this is your x max, and this is your omega. Okay, good. So at t equals 0, what is my position? At t equals 0, I have sine 0. So at t equals 0, x0 is equal to 0. Okay. Now find the time when the kinetic energy is twice the potential energy. Okay, that's my condition. Kinetic energy, I want it to be twice the potential energy. So let's look at the mechanical energy. E is constant, half k x max squared is equal to kinetic energy plus potential energy. So now kinetic energy, I'll write it as 2 us plus us. So this will give me 3 us. So which is equal to half k x max squared. So 3 us, and you remember us is just half k x squared is equal to half k x max squared. I simplify by k, simplify by half, and I find that x is just x max divided by square root of 3. So this is happening when the position is at x max divided by square root of 3. Now at x max divided by square root of 3, I can find my time. How do I find it? I will say that, well, it's equal to x max sine 10t. Basically, I'm just using this. Okay. Now, if I simplify by x max, now I have to solve this problem. Sine 10t is equal to this. That means 10t is equal to sine inverse of square root of 3 divided by 3. How much is sine inverse of square root of 3 divided by 3? Take your calculator and you tell me, how much do you get? Hello?
Yes, doing it.
Okay.
It will be 35.26.
35.26.
36.
5.3, let's say degree, right?
Yes.
Now I have to put it in radian because my omega is in radian per second, okay? So I have to put everything in SI units. So how much radian? So you know that 180 degree, of course, is pi radian. So that means here you will have how many radian? 35.3 divided by 180 multiplied by pi. So if I
0.6 pi.
0.6 radian. So that means your time will be what? 0.06 seconds. Because here omega is in radian per second, this is in radian. So of course t is in seconds, and you get your answer here. Okay. So in physics 102, inshallah, this will be your daily life because you will be solving, you know, wave, transverse wave, and longitudinal waves. Okay. But in physics 102, I will put some, you know, some spices. She's a little bit different. Okay. Good. Okay, this is straightforward. I will skip this. Now let me go to this problem. I have an oscillator which consists of a block attached to a spring, and I give you the spring constant. Again, m k. Okay, and I give you k here. K is equal to 400. At some time, the position measured from x0, so basically 0 here. So of course, my system is oscillating between x max and minus x max. Okay. And at some time, I have measured the position, the velocity, and the acceleration of the block. The position is 0.1 with respect to 0. So the position is here, and it's equal to 0.1 meters. The velocity is minus 13.6 meters per second, and the acceleration is minus 123 meters per second square. First question, what is the frequency of oscillation? So how can I get the frequency of oscillation? You know that omega is square root of k divided by m. I know k, but I don't know m. So I cannot use this formula because m is a second question. Okay. And by the way, frequency f is just omega divided by 2 pi, right? So if I get omega, I will get the frequency in hertz. I just divide by 2 pi. So that will not help. So what should I use? Yesterday, I told you that the signature of a simple harmonic oscillator is at any time the acceleration is minus omega square x. How do we get it? You know that x at any time is x max cosine omega t plus 5. What is the velocity? I take the derivative, dx over dt. Of course, chain rule, I will have minus, derivative of cosine is minus sine, omega will come out, and I will have x max sine omega t plus 5. And I told you that this amplitude V max is just omega x max. Write it down, it will come in your exam. Now, if I take the second derivative, I find the acceleration, which is the derivative of velocity with respect to time, or second derivative of position with respect to time. I'll have minus, the omega will come out again. I will have omega square xm cosine omega t plus phi. And this is just x. So the acceleration at any time is just minus omega square multiplied by the position at that time. This is a signature of a simple harmonic oscillator. Wherever I have second derivative of position, which is acceleration here, minus a positive number multiplied by the function, which is here my displacement, I have a simple harmonic oscillator because I have a restoring force or a restoring torque. Okay? So here I have a restoring force. So I will just say that A, which is minus 123 meters per second square, is just minus omega square multiplied by x at that time, which is 0.1. So I know what is my omega. Omega will be just square root of what? 123 divided by 0.1. Okay, and that will give me omega. And once I get omega, I can get the frequency, which is omega divided by 2 pi. Okay. Now, second question, find the mass of the block. Easy. Now I have omega, I know K, so the mass is known. Mass, you know that K is m omega square. So mass is just K divided by omega square. So write down this. Okay? For a block attached to a spring, this is just, you know, omega is square root of K divided by m. So three ways, this is exactly the same. So I know K, 400, I know omega from the previous question, I can get the mass of the block. Now, finally, what is the amplitude of the block? What is the amplitude of the motion? I will use conservation, mechanical energy. Mechanical energy is half K x max square. And it will be equal to kinetic energy, half mv square, plus spring potential energy, which is half K x square. So I know, of course, m. I know the mass of the block from the previous question. I know V, it's given here, minus 13.6. I know K, of course, I know X, so my only unknown is XM. Okay. Step by step, and you catch your bird. So this is a omega, and I get it in radian per second, and I divide by 2 pi, and I get my frequency. Once I get the omega, well, I know that for this, I just have this. So mass is equal to K divided by omega square. So the mass of my block is 0.325 kilogram. And then finally, I use conservation of mechanical energy. I know K, I know M, I know V, I know K, I know X. The only unknown is X max. Okay. And yesterday I told you that, of course, let me write it this way. K divided by M is omega square, right? And then we said that omega square X max is equal to V square plus omega square X square. Okay, this is just coming from the conservation of mechanical energy. If I divide by the mass and I simplify by the half. Okay. K divided by M will be omega, so I will get this. This is also very useful sometimes. You know, write it down. It will help you. It's just another way of saying that I have conservation of mechanical energy. And I get my X max, which is 0.4 meters. Okay, subhanallah al-azim. I want you to solve this problem. It's already solved in the previous sections. Okay. I can skip it. Okay, let me go to a physical pendulum here. I already solved it also in the previous section, so you can watch the recordings. But let me just do it in the 3 minutes which are remaining, inshallah. So we have a physical pendulum. You know that we know a simple pendulum. Simple pendulum is simple. Rod, massless, length L. The whole mass is focused at the bob M. So the rod is massless. And I told you that the period for a simple pendulum is just 2 pi square root of L divided by G. And omega is just square root of G divided by L. Okay. Good. Now here I have a physical pendulum. Physical pendulum, we demonstrated in class that the period T is 2 pi square root of moment of inertia of the physical pendulum divided by mgh. Okay. I is the moment of inertia of the physical pendulum around the pivot point. Okay, not around the center of mass, around the pivot point. So you have to use parallel axis theorem. And h is like the h in the parallel axis theorem. It's the distance between the center of mass and the pivot point. Here, I gave you a period t, and the period t is when the pivot point is here at r divided by 2 over the center of mass. So h is r divided by 2. So this is a pivot point here. Okay. It's a physical pendulum. Physical pendulum is anything, any object with a complex distribution of matter. I fix a pivot point and I just use small angle approximation. I deflect it a little bit and I release it, and it will be rotating around this point. Okay. And the period is t. Now the question is, what is the period if the pivot point is not here anymore, but the pivot point is at the rim, is here? So if the pivot point is here, and I deflect it a little bit, okay, now I will have an oscillatory motion, and of course it's a simple harmonic motion. Okay, now here the period is here, t. Now what is the period here, t prime? Is it equal? Is it 2 times t? Is it t divided by 2, etc., etc.? Let's calculate it. So t is 2 pi square root of moment of inertia. Now what is the moment of inertia? I have to use parallel axis theorem. IO is moment of inertia around center of mass plus mh square. Moment of inertia around center of mass, it's a solid disk, a uniform solid disk. What is the moment of inertia? Half mr square plus mh square. What is h? H is just r divided by 2 square. So if you do the calculation here, you will find what? 3 over half mr square. So moment of inertia is 3 divided by 4 mr square divided by mgh. Mass of the pendulum is m, g is g, we are on Earth, and h here is r divided by 2. The m simplifies, r simplifies, and I have 2 here. So I'll end up with t is 2 pi square root of 3 divided by 2 rg. And this is the period of the pendulum. Okay. So here, t prime will be the same actually, essentially. You can use the same. You say t prime, it will be 2 pi square root of the new moment of inertia divided by mgh. But here the h will be r. H here is r. And you will find that it's the same. But here I have to use parallel axis theorem. So you will find that t prime is equal to t. It will be just this. Okay, so they are equal, so this is it. Changing it, we did not change it for this geometry. Okay, it's almost time, or it's already time. Let me stop here. Now, let me just finish by this. Now, if I ask you a question, a simple question, what is the length of a simple pendulum that will have the same period? You will just say that, you know, is 2 pi square root of L divided by G. So this L here should be equal to 3/2 of R. So the simple pendulum that will give me exactly the same period will have a length equal to 3/2 of R. L is equal to 3/2 of R. Okay, so I wanted to solve this. I solve it with other sections, okay? So you can watch, I will post all the free videos. You can watch them at your ease, and I will post also some mock exam, inshallah. Anyway, it was a pleasure teaching you Physics 101. I hope you grew physically, mentally, spiritually, and you grew also financially. Okay, that's the objective. It's not